Hello, in this video I'm going to tell you more about our research project Smart Contract Vulnerability Localization and Detection using Pre-trained LLMs. First of all, let me tell you a bit of a story. Imagine Bob wanted to send money to Alice. In a usual financial system, what happens is Bob goes to a bank and then deposit his money. Then bank takes the full custody of this money and then only they transfer this money to Alice. In this case, we needed an external third party where we could verify. But imagine what if a program could do this? In the smart contract world, Bob can transfer money direct to Alice without any trusted third party. Smart contracts are self-executing agreements on blockchain, typically written in Solidity. In this case, we have to remember that the bytecode of the smart contract is written in a blockchain and it's publicly accessible to basically anyone. Great power comes with problems, right? In this case, that is exactly what happens about a month ago. CETUS was a DeFi exchange. This is almost exactly something that's similar to bank, where you can transfer money between people. But the problem was this CETUS protocol was exploited, and the underlying vulnerability was an arithmetic vulnerability, and this resulted $223 million worth of funds being lost just because of a small smart contract vulnerability. This is why we really need security for these smart contracts. Trust and security is essential to future adoption of these smart contracts. That is why we were motivated about a year ago to figure out smart contract vulnerabilities and also localize them within a smart contract code. When it comes to research objectives, so our first research objective is to develop a high quality Solidity dataset with line level vulnerability annotations. We were planning to design a neural architecture using pre-trained LLMs for accurate localization across multiple vulnerability types, and also we tried to enhance multi-label vulnerability detection through some sort of a transfer learning framework, leveraging localization insights that we derived in the second step. When it comes to our methodology, I can categorize into three parts. So first one is exploration phase, where we tried out multiple architectures and also we curated a data set and we prepared it. And also our project needed huge amount of compute. We were able to secure some compute from AWS. We got a grant of $5,000 worth of AWS credits. And also in the second step, we were running some experiments, which I will go into details in a minute. So in these experiments, we usually designed them, implemented them, then tested what are the results, and then we evaluated, and again that evaluation resulted a new design. So we iterated through a couple of cycles in this stage, and right now we are in the knowledge dissemination phase. When it comes to methodology, one of the key things that we did was dataset preparation. So when it comes to our dataset, we had 1125 smart contract, and there were 14 vulnerability classes in our case. This is a distribution of vulnerabilities, and this is our model architecture. So our model primarily consists of two sections. So one is for localization and the second one is for classification. When it comes to localization, what we do is we use the existing pre-trained LLM, and then we get the last hidden status of the LLM, and then we pass it down to a gated recurring unit, and then we do something called bidirectional adapter, and then we pass this down through feed forward projection and also BC with logicless to reduce the dimensionality, and then for each line we will get a result whether it's a vulnerable or not. Right after we get this localization model figured out, then we freeze up until this bidirectional adapter and we use that for the classification. So in there we basically did compare two configurations. Then we have like bidirectional gated recurring unit, and then we pass it to feed forward projection and we see it logic loss to reduce the dimensions, and at the end we will get results out of let's say out of 14 vulnerable classes plus non-vulnerable type, and we will get the classification of the vulnerability. So this is our overall architecture, which I will explain little by little. And when it comes to the primary result, this is our results compared to existing tools. So a couple of these tools are day to day used by many people throughout the world. So Security, Mrithil, Slither, Manticore are very common tools, but they do not give very good results. our results are comparable to all the literature out there. But we should mention that this Mando HGT and Mando project, which are based on like GNN's graph neural networks, actually outperforms our results in most vulnerabilities. Believe that if our architecture is extracted into a better, bigger model, then this will actually perform better, because we have only used 14 billion model at most. So this is our primary results. To train and validate, we basically use 1125 Solidity smart contract set, and we did tenfold cross validation, where we use 9 to train and then validate using 1. And also when it comes to testing, did that using 350 smart contracts of with 7 vulnerability types, which has been used in multiple literature. So this is the 7 vulnerability types that are out there. And when it comes to infrastructure, we used A100 GPUs plus A40 and A10 instances from AWS and RunPod using our AWS credits. And when it comes to evaluation metrics, we primarily use F1 scores and top at K scores. And because we did tenfold cross validation, we had to do statistical checks, Wilcoxon test and Friedman test. Let me go to each and every experiment. Let's first go to our choice of LLM. So in our end result was to select a DeepSeek R1 distilled Qwen 14 billion model. So to figure this out, we actually ran an experiment across like 10 folds with multiple LLMs. I mean, we have shown results from the best 3. We used multiple models: CodeGen, DeepSeek R1 distilled Qwen 14 billion, and also Qwen 32 billion one, and also DeepSeek distilled Llama 8 billion model. So out of these, you can see that the DeepSeek R1 distilled Qwen 14 billion model outperformed here with higher F1 scores and also top 1 and top 3 scores as well. Also, when it comes to this pre-trained LLM part, we had option to use a prompt with our smart contract code when we inject this to LLM, and also we had option to not to use a prompt. These are the results based on without prompt versus with prompt. As you can see, this 7.4% increase if we use the prompt. This results as proper prompt engineering, it will actually improve the results. We also did ablation test, where you use a reason based LLM versus non-reasoning based LLM as well. Our ablation test was done with a DeepSeek R1 distilled Qwen 14 billion one, and also CodeGen 16 billion model. When it comes to F1 score, you see 16% increase when you have a reasoning model, and also top 1 accuracy, you can see 11% more accurate results from DeepSeek. And when it comes to model architecture, the next choice that we had is introducing a GRU compared to linear models that have been used in the literature. So this addition of GRU was done using like our intuition, but we had to confirm this using experiments as well. So this is the experiment that we ran with a linear model versus GRU with the same configuration. So in that case, we see 5.83% better F1 scores in like GRU. In our transfer learning task, you have used 2 configurations. So the difference in here is adding an encoder layer in between like frozen model and also bidirectional GRU. Let's have a demo of the tool that we built using our final research project. Let's actually upload a .sol file where we can see what are the vulnerabilities within. In this case, now it's been verified, and now we have the report itself. So in here, we can see that we have identified there's a reentrancy vulnerability within this one, and also we can see there's an unchecked external code. So it's in the same line just as reentrancy, which is causing the both problems. And also there's an integer underflow within this line, which someone can cause unwanted behavior throughout the code. So this is an example how you can upload a smart contract file and get the vulnerabilities within it using our tool. When it comes to future work, we believe that if we expand the dataset size, I mean, we only have 1125, right? So if we improve the dataset, we'll perform better. And also if we use a bigger and better model with a more reasoned model, this will definitely perform better. As of now, we have used zero-shot prompting. But if we have few-shot prompting, where we introduce couple of vulnerabilities within the prompt itself, we believe that it might perform better and will work better in unseen vulnerability types, and also fine-tuning this LLM before we use it within our system. We believe that will perform better in most cases. As of the applications of our product in future, we believe that, let's say in a VS Code editor with some AI based editor like Cursor, they can actually develop a real-time inferencing model based on our architecture to have give suggestions about vulnerabilities within the editor itself. And also in the smart contract domain, there's a section where we call smart contract audits, where people manually verify the whole smart contract code. We believe that this like a better model can be useful to identify, give suggestions to these smart contract auditors as well. So this is about our whole research project, and thanks for your time.